Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is Sintering of ceramics, its fundamental aspects and mechanisms, and some processes for fabricating porous ceramic materials. In the last lecture, we discussed the following aspects. The basics of cellular ceramics fabrication were discussed, and main emphasis were put on the processes of powder consolidation and forming, the main additives which are commonly used for fabricating porous ceramics, and also the die compaction for green body fabrication for fabricating porous ceramics were discussed. The main topics which will be covered in this lecture include the sintering of ceramics and stages of sintering. As I already mentioned in the previous lecture, that although sintering of ceramics is a very vast topic and it is used mainly for bulk ceramic fabrication. However, several porous ceramic fabrication processes also include sintering, such as using pore formers or freeze casting, and that is the reason that a very basic description or discussion of the sintering of ceramics will be discussed in this lecture. Finally, we will learn about two processes for fabricating porous ceramics. One of these is partial sintering and the second one is freeze casting. The main keywords for this lecture are sintering of ceramics, solid state sintering, liquid state sintering, vitrification, viscous sintering, stages of sintering, partial sintering and freeze casting. So, the first question that comes at this stage is what is sintering of ceramics or what is sintering as such. So, we learned in the previous lecture about the green body fabrication either by cold isostatic pressing or by using uniaxial pressing in a die. Now, this green body after its fabrication, it contains a significant amount of porosity and there is no real bonding between the particles, and as such the green body lacks in strength. So, sintering is typically employed to increase the bonding between the particles and also to impart strength to the porous body. Now, in bulk sintering, the aim is to attain almost theoretical density, that means even more than 99%, 100% almost. And in case of porous ceramic fabrication, although the aim is to have significant amount of porosity, but as I already mentioned that this porosity is provided by the pore formers. That means, we use certain pore formers like some kind of polymer wax or some other, like in freeze casting we use ice templating as pore formers. So, the idea is that the pore formers will provide the porosity, but the ceramic rich regions, that means the surrounding ceramic regions should be as nearly dense as possible to provide high amount of mechanical properties. Because if the ceramics are not well bonded to each other through strong bonding, then the porous body will again have poor mechanical properties and also the microstructure will not be well defined, which are again not expected. Now, in sintering there are again different variations are there. The first process which is done is called solid state sintering, and this is also the process which is typically employed for porous ceramic fabrication. In sintering, the material or the green compact is heated to a high temperature, which typically ranges between 0.5 to 0.9 of the melting point, and because of this high temperature and for the duration of the time for which the green body is held at this high temperature, significant amount of mass diffusion takes place and that actually gives rise to good bonding between the individual particles. Now, in case of solid state sintering, it is called solid state because no liquid is present and the main mechanism of atomic or bond formation is the atomic diffusion. Now, this is, as I already mentioned, this solid state sintering process is most commonly used for porous ceramic fabrication. There are other variants of the sintering process like liquid phase sintering. In liquid phase sintering, which is again mainly used for bulk ceramic fabrication, a small amount of liquid phase is typically introduced. This liquid phase may be introduced as an additive, or it might also form because of some eutectic reaction between the constituents of the initial green body. Now, the idea is that this liquid phase will actually, it is generally formed in very small amount, a few volume %, and this liquid phase will actually enhance the rearrangement of the particles, and this way it will provide densification at a lower temperature. But it might have some limitations, because when further, because ceramics, as we know, they are very attractive materials for high temperature applications, and because this liquid phase sintering, this liquid phase might form at a lower temperature, that might actually reduce or restrict the high temperature applicability of the ceramics such developed. There are also other less established processes or lesser established processes like for vitrification and in viscous sintering. But as I already mentioned, I reiterate that for porous ceramic fabrication, it is the solid state sintering which is the most important process, and it is rarely liquid phase sintering or vitrification is performed for porous ceramic fabrication. Now, all these processes which I have mentioned until now, the solid state processing or liquid state processing, whatever has been mentioned, these are all fabricated typically under no applied pressure, that means it is pressure less sintering. But there are also processes where again some extra pressure is applied to actually accelerate the densification process, and these processes are known as sintering under applied pressure or pressure assisted sintering. But again, this pressure assisted sintering is a common process for bulk ceramic fabrication, and again for porous ceramic fabrication it is very less employed, and again for porous ceramic fabrication it is mainly the solid state sintering without an applied pressure in a suitable atmosphere is commonly used. Pressure sintering has the advantage that because of the applied pressure, the driving force for sintering is reduced, and as a result the sintering is carried out at a lower temperature, and also less amount of time at that high temperature is required. And this has benefits because a combination of lower temperature with lesser amount of time will actually lead to a less amount of grain coarsening, which can lead to better mechanical properties. At the same time, this has the advantage that the process becomes much more expensive, because the equipment which is commonly used for pressure sintering is a very kind of extensive equipment, because you typically require a very high amount of temperature and high pressure combination, and that requires very specific materials and also very specific atmospheres. Whereas, in case of pressureless sintering, it can be performed in a typical muffle furnace, for example, for an oxide ceramic, or in a normal tube furnace for carbides and nitrides, where basically a controlled atmosphere is required. So, a basic graphical description or graphical differentiation between pressureless sintering and pressure assisted sintering is shown in this slide. So, as I already mentioned, a pressureless sintering you do not require any pressure. The grain body is put under the, if some atmosphere is required as such for carbides and nitrides, then this atmosphere is provided, and then the material is actually heated to the required temperature, held there for certain amount of time which is pre-established, and then after that time it is cooled down to the room temperature, and it is expected that some amount of, because of this pressureless sintering, it is normally very difficult to actually obtain 100% densification. So, there remains some porosity between the particles as shown by these white dots in this schematic image. In comparison, in pressure assisted sintering, typical examples are vacuum hot pressing or hot isostatic pressing or spark plasma sintering. In this case, actually you typically apply a combination of pressure and temperature, and as I mentioned, because of this combined application of pressure and temperature, the temperature requirement is lower than pressureless sintering, and also the time at this high temperature is also much lower. In case of SPS for example, or spark plasma sintering, it can be even only a few minutes, and which can actually lead to very good mechanical properties, because we have a very nice bonding between the particles, because it is almost 100% dense, and also because the combination of temperature and pressure are low. So, there is reduced grain coarsening, which both lead to good mechanical properties. But again, as I mentioned several times, for porous ceramic fabrication, our interest is on the left hand side, this pressureless sintering. Very rarely pressure assisted sintering is used for porous ceramic fabrication. Now, we have discussed that sintering is a process through which these green bodies they attain the high density. Now, there are and the basic mechanism of sintering, as we already mentioned, it is the atomic diffusion. Now, this sintering has individual processes or sintering mechanisms, and several such mechanisms have been identified, and the 6 most important mechanisms are shown in this schematic diagram over here. Now, these 6 mechanisms are identified as surface diffusion mechanism number 1, then lattice diffusion, as you can see it takes place from this point to this point like this, the lattice diffusion, then vapor transport, grain boundary diffusion, and lattice diffusion from the grain bound. That means, the process number 2 was basically lattice diffusion from the surface, and process number 4 or other 5 is lattice diffusion from the grain boundary, and there is also one mechanism called plastic flow. Now, these mechanism actually in many cases they actually occur in unison. That means, not only one mechanism is operative at any particular temperature or pressure, actually several or more than one mechanisms can actually operate together. Now, all of these mechanisms, all of these sintering mechanisms have the function that they actually provide an increase in the neck growth. That means, you have the neck region between the particles and individual particles in the green state, and these sintering mechanisms they actually provide the neck growth, and because of this neck growth actually the bonding between the particles enhance, and that actually leads to higher strength of the porous body after sintering. Now, these mechanisms or these 5 or 6 mechanisms they actually occur in different fashion. Out of these mechanisms, mechanisms 1, 2 and 3, that means surface diffusion, lattice diffusion and vapor transport, they actually lead to neck growth without densification. That means, these 3 processes they actually lead to coarsening, but without any reduction in the porosity. Whereas, in case of the mechanisms 4 and 5, that is the grain boundary diffusion and lattice diffusion, it actually leads to both neck growth and your densification. That means, these 2 processes are very important for actually the reduction of the porosity, and all the processes they actually lead to the growth of the neck region. And the final, the 6th process, that is the plastic flow, this is actually more common for metallic materials, where this plastic flow actually leads to more densification by movement of dislocations. And as I mentioned, these 6 processes they actually several processes actually work together to actually give rise to the final sintering of the material. And sintering also occurs in several stages, as has been mentioned or schematically shown in this diagram over here. So, as is shown in this diagram, in stage A we have the green body. That means, after the green body fabrication we have large amount of porosity and only some mechanical contact between the individual particles. At this stage, as I already mentioned in the previous slide, we have around 60% porosity. If the particles kind of in the densest packing stage, we have around 60% porosity. And then as we increase, as the sintering actually progresses, the image B actually shows the first stage of sintering, and in this case, as you can see, there is particle coalescence actually occurring, and this, so initial neck formation occurs between the particles, and the pore volume which is actually occurring between the particles is reduced a bit. So, after this second stage, as you can see over here, we have the density actually increases or densification by a small amount up to around 3 to 5% densification increases. So, after stage B we attain somewhat in the range of 65% densification. As sintering continues even further, then stage C initiates, and in stage C we actually see that the pore regions between the individual particles they actually reduce, the particles they undergo coarsening, and the pores they actually form kind of interconnecting pores between the between three particles they actually form, and this way we have the intermediate stage of sintering, and this intermediate stage actually takes place over the longest period of time, and after this intermediate stage we attain a densification in the range of 90%. So, this intermediate stage is the most important stage of the sintering process. And finally, in stage D, at even higher, even longer sintering time or temperature, actually these individual these interconnecting pores they actually kind of pinch off, and this actually forms small pores at the particle corners. So, as you can see, so this is one pore, this is one pore. So, this individual pores are present at the particle corners, and at this stage or at the end of this stage we attain more than 99% densification depending upon the particle upon the material and the selected sintering conditions. So, again if we see that how the evolution of the relative density or the densification actually varies over sintering time, we can see here that again these three stages are marked over here. So, initially we have at the 0 time we have the green body. This green body is again this is what we obtain after the initial uniaxial pressing or cold isostatic pressing, and then in the initial stage of sintering where only neck formation occurs between the individual particles, we have up to around 3 to 5% densification. That means, the initial density was up to 60% and or densification, and that actually increases to in a range of around 65% after this initial stage, and then the longest period or the highest or the most densification occurs in the intermediate stage, where we see that it is around up to 90% or 95% even the densification increases, and then the final stage where the interconnecting pores actually detach and small pores remain at the particle corners, and that we attain in the final stage of sintering. So, again these three stages of sintering are shown in this slide. So, with these we actually I mean this sintering is a very brief very vast subject, and and for that, and that is not the aim of this course to discuss a lot about sintering, but some basic introduction of the sintering was required to understand the future steps or the other porous ceramic fabrication processes. So, that is why I just introduced the concept of ceramic sintering in a very brief fashion, and for a more detailed discussion we should the students should refer to the references which are cited in this lecture. So, after this brief description or introduction to sintering stages and sintering processes, the next aim is to briefly learn about the individual processes or some individual processes which are commonly used for fabricating porous ceramics. So, again before I go there, so again this is in this slide it is shown that how actually at different stages of sintering how the microstructure actually evolves. So, we can see that in the stage 1 or after the stage 1 we have a lot of pores, and the particles are also kind of fine particles, and as we move with the sintering time there is particle coarsening occurring, and the pores are actually kind of joining together and forming interpenetrating or interconnecting pores, and then after the stage 3 as you can see over here there is significant grain coarsening has occurred, and also the pores they have they are not interconnecting anymore, and individual pores kind of formed at the grain boundaries. So, this is a kind of pinch off and form individual isolated pores at the grain boundaries, and the grain size has increased significantly. Okay. So, now about the fabrication processes for porous ceramics or cellular ceramics, which is mainly called as porous ceramics. So, the first and the simplest process is actually the partial sintering. So, this again I can easily go back to the previous slide and explain what is happening over there. So, the basic idea is that in partial sintering we do not sinter the material to its final densification. That means, again the process steps are shown over here. The basic process steps are same as we discussed in the previous lecture, that means the mixing of the ceramic powder and the additives. Then we fabricate the green body either by cold isostatic pressing or uniaxial pressing, and then we apply partial sintering. That means, we can actually imagine this as that we do not continue the sintering to the stage 3 as shown in this slide, or rather we stop the sintering somewhere in the stage 2. That means, we can actually by doing this we actually restrict the continuous this kind of this pinching of the isolated pores, and here actually basically we maintain the high amount of porosity in the green body by not sintering to the complete or 100% densification. So, this process has the advantage that it is a very simple process, and also it is very cost effective because you do not need to go to very high temperatures or very high holding times. But the drawback is that because you are not sintering the particles, so the interparticle bonding is not that strong, and that is the reason that these porous ceramics after partial sintering they may actually lack in the mechanical properties. And also there is, I mean, we can get up to around 60 volume percent porosity in this particular case or in that range, and there are many pores which are actually closed pores, and this the process parameters to be used for this partial sintering again depends upon the initial material selected, and also the parameters like temperature, pressure, atmosphere and the holding time at the high temperature, they actually play a big role in actually defining the final porosity in these bodies. So, there are many examples or many literature articles where porous ceramics have been fabricated by using this technique, this partial sintering technique, and some examples are being shown over here where beta silicon nitride was sintered at 1750 degrees Celsius for 2 hours. So, if it is and that actually gives us to this elongated pores, and also this lot of this high amount of interconnecting pores between the individual this elongated beta SiO2 particles. So, after this simple process of partial sintering, the next process which is commonly used, rather very commonly used these days, is known as the freeze casting process. So, freeze casting is a rather new process for fabricating porous ceramics developed mainly in the last around 15-20 years. So, this is a very well established process in the meantime, and it is also a very simple process which is again used for fabricating biomimetic materials. It means materials which actually mimic the biological materials like nacre or shells. So, in those cases actually this freeze casting actually plays a very important role, and this process actually again for this process one requires a ceramic slurry as is being shown over here. So, this is a special type of container is fabricated where, because the main process is that in this freeze casting process the main mechanism is that ice crystals are actually nucleated and made to grow along one particular direction. That means, as you can imagine over here, if a container is made in such a way as is being shown over here, that the bottom is made of a very high conductive metal like copper. That means, this metal over here is it's a copper bottom or copper base, and the surrounding is made of a low conductivity material like some polymers, like some kind of polymer, something like that, and then in this container a ceramic slurry is taken. That means, a ceramic particles, so there can be any ceramic particles. Many ceramic particles have been developed by freeze casting by now, like alumina, silicon nitride, silicon carbide, boron carbide. So, they have quite a lot of porous ceramics have been fabricated. So, you basically take porous ceramic slurry, that means some porous ceramic powders in some water, adding some dispersants and some binder, and then this whole container is actually put under a low temperature, that means a sub-zero temperature. And then what happens, because now this whole thing is put in a sub-zero temperature, so then actually there will be ice crystals growing, and because the ice crystals, the temperature gradient is along the vertical direction, because you have the cold plate at the bottom and then the surrounding is made up of the low conductivity material like polymer. So, the heat will be ejected along the vertical direction, and because of that the ice crystals, as is being shown in this schematic diagram by this blue growing faces, So, the ice crystals will tend to grow along the vertical direction, and then when the ice crystals are growing along the vertical direction, what is happening? The ice has a tendency to actually reject the solute particles. That means, the ceramic particles which were in the slurry, they will be rejected, and these ceramic particles, they will actually assemble between the two growing ice crystals. So, as you can see over here, this after this freezing stage, you have the ice crystals, and between the ice crystals you have the ceramic particles assembled together. So, this is basically the phase diagram shown of water as is being shown over here, and as we know that this is being carried out. So, after the first stage, as you can see, the temperature is more than at this first stage, initially we are at this point, that means at atmospheric pressure and temperature at room temperature, and now this is the freezing stage I just discussed, where what you do at the same pressure we simply reduce the temperature to a sub-zero level. It can be like minus 10 degrees Celsius, minus 30 or whatever, and this sub-zero temperature what you select for this freeze casting process has significant influence over the final microstructure, we will see in the next slide. So, then after you reach this point, after this freezing stage, then the stage is very important. We do not let the solid to kind of again this solid to again transform to liquid, rather the pressure is immediately reduced to below this point, below this, and to that means this ice crystals which have developed over there, these ice crystals are made to sublimate. That means the pressure is reduced significantly, and to this point where the ice crystals sublimate, and when the ice crystals sublimate, actually we obtain the porous body. So, this is the idea that this first you assemble or arrange the ceramic particles between the growing ice crystals, and then after that this ice crystal is sublimated, and by doing that we obtain the porous body. But this is again the green body, because now the ceramic particles are not bonded to each other, it is a green body which lack in strength and stability. So, the next process is that after you obtain the green body, this green body is sintered again by pressureless sintering, and again if it is kind of an oxide ceramic, we can do it in air, and if it is kind of a carbide or nitrate ceramic, we have to use some special atmosphere. But the main thing is that this green body is sintered, and after sintering it attains its mechanical strength, and we obtain these ice crystals where the initial ice crystals were there, they actually give rise to the porous regions, and in between the porous regions the ceramic particles they actually bond together, and we obtain a very nice sintered porous ceramic body. So, this porous ceramic, I mean the structure of the porous ceramic depends upon several factors. One of the factors is that how much of the ceramic has been added in the initial slurry. That means, the more ceramic slurry is added in the initial slurry, the lesser will be the porosity. Also, the ice front velocity plays a very important role. That means, the lower the temperature of this, that means the lower this freezing temperature as is being shown over here, the lower the freezing temperature, the more will be the nucleation. That means, there will be more nucleation of these ice crystals, and that will lead to a more finer microstructure, and the higher the sintering, higher the freezing temperature, there will be less nucleation and more growth, and that will lead to actually coarser microstructure. And it also makes sense that because this whole thing, the growth of the ice crystals is controlled by this temperature gradient from this cold plate to the top side, and as we move upward the temperature gradient actually decreases, and as a matter of fact that actually makes that at the bottom portion we have a very very fine structure, because more ice crystals nucleate over there, but as we move upward the nucleation rate reduces and the ice crystals basically grow, and as a result that as we move upward the structure becomes more and more open structure. That means, towards the bottom phase or the bottom we have a very fine structure, very fine porous structure, and as we move upward it becomes a kind of a coarse pored structure. So, typical images are being shown over here. So, as you can see over here that as these are actually microcomputer tomographic images. So, these are basically the porous ceramic bodies. So, these whatever you see over here, these are the porous ceramic bodies, and then different tomographic slices were taken. As you can see, these porous ceramic bodies typically have a lamellar structure, because ice crystals they have different because of the C by A ratio of the hexagonal ice crystals, they are different, the growth rate is different, and that actually gives to different this lamellar structure. but as we move from top to bottom as is being shown over here. So, initially we have over here, as you can see, they are very fine structure as we just mentioned, and as we move upward in this direction, you see the structure becomes more and more open and it becomes a coarse pore structure. And if you see if you see at this surface, for example, at a direction normal to the ice crystal growth, you have such a very nice lamellar structure. Now, freeze casting has become very popular these days because it has many advantages. First thing is that this is an extremely pollution free process, because we have only water as a solvent, and there is no burning of hazardous materials like some polymers or some like, as you will see in gel casting, for example, it can be hazardous for the environment and also for the technician or for the scientist who is working on the material. In this case, we have only sublimation of water or ice, and that is actually very environment friendly and less polluting. And also here actually we have no chemical reaction, it is only the whole thing is basically dependent upon the ice, first the formation of the ice and then its sublimation. That means it's very simple process, and also the pore size and the pore distribution can be varied over a wide range. That means simply by changing the amount of ceramic particles in the initial slurry or by selecting the freezing temperature in a proper manner, one can actually control the pore size and the pore morphology over a wide range, and these pores are all very much interpenetrating. That means there is a very nice connectivity between the pores, and that actually gives some applications like filtering and whatever very much possible. But this has one drawback, this freeze casting process has one major drawback, that is the thing, as we already see over here, that these pore structures are not isotropic. That means we typically have one growth direction of the ice crystals along the vertical direction shown over here, and that actually gives kind of a lamellar structure, and also along the growth direction we have kind of UD morphology, and that actually renders the bodies to very large amount of anisotropy. That means these porous bodies after freeze casting, they are not isotropic materials, they are very much non-isotropic or anisotropic materials. Okay, so with that we discussed two processes today, and in the next lecture we will move on and learn about some more processes like gel casting, replica techniques and so on. So, to conclude today's lecture, we learned about the basics of the sintering process, that how sintering actually imparts strength to the green body to improve the mechanical properties through bond formation by diffusion has been discussed. The different sintering processes like solid state sintering, liquid phase sintering, vitrification and viscous sintering were discussed briefly, and also the stages of sintering like the initial stage, intermediate stage, and the mechanisms of neck formation like the vitreous flow or lattice diffusion. So, all those things were discussed in brief detail. Finally, we discussed about two processes for fabricating porous ceramic bodies. One was the partial sintering and the second one was freeze casting. So, these were the content of today's lecture. I refer to the following literature. Among these, the book by Professor Rahman, The Ceramic Processing and Sintering, is a very nice book to learn about the fundamentals of sintering process, and this review article by Kota et al., this is a very nice review article on the various fabrication processes for porous ceramics commonly employed. So, in the next lecture, as I already mentioned, I will continue with some more fabrication processes commonly used for porous ceramics, like 3 processes will be discussed: gel casting, sacrificial pore forming agents and replica technique. Thank you very much.